Okay, so now let's look at the energy of a simple harmonic oscillator. So the energy is always potential plus kinetic. Potential energy plus kinetic energy. For a spring, and this is from General Physics 1, the potential energy is 1 half k x squared, where x is the displacement from this equilibrium position. The kinetic energy is always 1 half mv squared. So now we can plot the potential energy, and that is a parabola, like it is here. And then we can see that the potential energy goes from a maximum at minus a to a minimum here at 0 to a maximum again at a. And at all times, this sum, kinetic plus potential, is constant. Energy is conserved. That means this energy, total energy, is always constant. So this is the potential, this is the kinetic plus potential, which is 1 half mv squared plus 1 half k squared. That is a constant. What that means is that right here we have a harmonic motion, and this blue line is the potential energy as a function of time. The green line is the kinetic energy. At any point, if I add the value of the blue line with the value of the green line, I'm going to get this brown value here, which is the total energy, which is always a constant. The maximum occurs when when you have all potential energy, or the maximum for the potential energy occurs at the point where the oscillator is stretched the maximum, and the maximum for the kinetic energy, they occur at the points where the oscillator is moving fast. So when x is equal to plus minus a, that is when it is stretched the most, then that is the maximum of potential energy, and at x equals 0, that is the maximum of kinetic energy. Let's look at a simulation and see how this works. So let's remind ourselves this is an oscillator, and then let's pause now. So here we have position versus time, and here we have velocity versus time. You can see at this point, this is the maximum for the position. That is when you would have your maximum potential energy. Right here, when this is 0, you have your maximum for the kinetic energy. So now we can look at the energy versus time graph for the oscillator. Let's look at this, and let's look at a right here, and then you can see that at all times the blue line is the potential energy, and the blue line is the potential energy, the red line is the kinetic energy, and at all times it never goes above this value here. And you can see that they all add to this constant value, and they have this oscillatory motion. And when one is 0, the other one is maximum, and when the other one is 0, when the kinetic is 0, the potential is maximum, and when the potential is 0, the kinetic is maximum. Okay, so let's look at a simple question here. We have a block that oscillates on a very long horizontal spring. The graph shows the block's kinetic energy. This is the kinetic energy of the block as a function of position. Here you have the position. What is the spring constant? Is it 1 Newton per meter, 2 newtons per meter, 4 newtons per meter, or 8 newtons per meter? If you don't remember, remember that the force in a spring is minus kx, and this k is the spring constant. And the potential energy is 1 half kx squared, and the kinetic energy is just 1 half mv squared. Take a minute to answer this question. Well, we can see that the maximum amplitude is 2 or minus 2, right? And the maximum energy, the maximum kinetic energy is 8 joules right here. So the maximum kinetic energy is 8 joules, and that have to be equal to the maximum potential energy, which is 1/2 Ka squared. Remember, the potential energy is 1/2 Kx squared, and when x is maximum, then you get the maximum potential energy. So from this equation here, you can solve for K, and then you get that is 4 newtons per meter. So now we can play around and come up with a few equations for a harmonic oscillator. And so we know that the maximum kinetic energy is equal to the maximum potential energy. So from there, we can get the maximum velocity of the oscillator, which is the square root of K over ma. That is the maximum velocity. Using kinematics earlier, we found that the maximum frequency is 2 pi a over t. The maximum velocity is 2 pi a over the period, which is 2 pi fa, which is omega a. Right? Remember, the way we found that is that we wrote that x of t was equal to a cosine omega t. We took the derivative dx dt, and that gave me minus omega a sine omega t. And this is maximum when the sine is 1. So that gives me that V max is equal to minus omega a, the absolute value, which is this value here. So then from here we can find a few things. We can write that omega, the angular frequency, is the square root of k over m, and the frequency is, well, is omega over 2 pi, which is 1 over 2 pi square root of k over m. And the period is 1 over the frequency, which would be 2 pi square root of m over k. Okay, so we have a question here. A mass oscillates on a horizontal spring with a period of t equals 2.0 seconds. If the amplitude of the oscillation is double, the new period will be 1, 1.4, 2, 2.8, or 4. Take a minute. And the answer is 2. The period won't change, simply because the period does not depend on the amplitude. It only depends on the mass and the spring constant. Another question, a block of mass m oscillates on a horizontal spring with a period t equals 2 seconds. If a second identical block is glued to the top of the first, then the period will be, take a minute. The answer is 2.8 seconds, and that is because if we go back to our equations here, we can see again the period depends on the square root of the mass.